In October 2025, the universe went quiet. Interstellar comet 3IATLAS, a visitor from beyond our solar system, vanished without a trace after slipping behind the sun. But what followed defied explanation. Strange afterglows shimmered in ultraviolet light. Radio whispers pulsed through the static. Mars reflected a ghostly echo where nothing should have been. Instruments failed in perfect unison, and magnetic fields rippled as though something unseen had passed through. Was it destroyed, transformed, or simply hiding in plain sight? Tonight, we follow the evidence, the fading light, the spectral fingerprints, the invisible trail through solar wind and plasma. We will test the impossible and listen for what might still be speaking across the void. Because if the afterglow is real, it means 3IATLAS never left. It means something alien is still out there, moving, breathing, and waiting to be found. When a comet disappears, the story usually ends there. It fades into the glare of the sun or breaks apart into a fine mist of dust, and astronomers write the final line in its logbook. But with 3IATLAS, the third interstellar object ever seen, that moment of disappearance did not feel like an ending. It felt like a pause. Something about its exit did not match the silence that followed, and as the days passed after its vanishing point, small fragments of data began to hint that maybe, just maybe, the comet had not gone at all. Maybe what remained was an afterglow, faint and ghostly, still alive in the void. For weeks, telescopes across the world tried to reacquire it. When the object slipped behind the sun, astronomers expected it to emerge again, dimmer but traceable. It never did. The sensors showed only static, faint blurs that seemed to flicker in place. Yet those same instruments began to detect a residual light, as though the empty region where the comet had once been was still reflecting energy. It was not a clean absence. It was as if something invisible lingered there, holding the memory of brightness long after the source was gone. That idea gave rise to what some call the Afterglow Hypothesis. It suggests that under certain cosmic conditions, a disintegrating interstellar object might leave behind a persistent field of charged dust and vapor that glows faintly as it interacts with solar radiation. It is not the comet itself, but its ghost, lit by the sun's breath. In other words, the vanish is not the end. It is the start of something stranger. When scientists reanalyzed spectroscopic readings from the last few hours before disappearance, they noticed an irregularity. Certain emission lines that should have collapsed with the comet's fading instead persisted for hours, possibly days. Oxygen and carbon traces hovered where there should have been silence. The instruments were not lying. The signals pulsed faintly, like an echo repeating in a vast, empty hall. The comet was gone, but its chemical afterimage was still whispering. Some argued this was a simple case of residual scattering, the sun's light bouncing off dispersed dust. But the geometry did not fit. The brightness curve decayed too slowly and too smoothly. Others suggested plasma interaction. As the comet evaporated, it might have released ions that the solar wind later excited, causing a faint, ongoing emission. That could explain why some telescopes detected ultraviolet flickers where no visible object existed. But even that left questions. The signals seemed too organized, too consistent with a moving source. It almost behaved like a body continuing along a path unseen. If 3IATLAS truly left an afterglow, it would mark a new class of transient objects, one that blurs the line between matter and memory. Unlike traditional comets that burn out, this one seemed to have left behind a map of where it had been, drawn in charged particles and faint light. And what makes that even more intriguing is timing. Just as the residual glow was detected, the sun unleashed a burst of charged plasma, one of the most intense coronal streams recorded that month. If that stream crossed the region where 3IATLAS dissolved, it might have reignited the dust like embers catching wind. Or imagine that. A comet from another star system torn apart by solar heat, its fragments drifting silently until the sun's next breath made them shimmer again. The glow would not be the comet itself, but the solar wind remembering it. That poetic image drives both scientists and dreamers to keep looking. The theory may be fragile, but it is seductive. Because if the afterglow is real, it means the comet still speaks in light, even after its body has died. As more data came in from Mars orbiters and deep space probes, analysts noticed one more detail that refused to fit the narrative of disappearance. The Mervin probe, orbiting Mars at the time, picked up a minor spike in ultraviolet radiation 2 days after 3IATLAS supposedly vanished behind the sun. The timing matched almost perfectly with the moment the solar stream reached the region where the comet's trajectory would have intersected the inner solar wind. The spike was small, almost ignorable, but persistent. No solar flare or meteor trail explained it. It was simply there, like a breath caught in the background of cosmic noise. Some researchers dismissed it as coincidence, but others wondered whether MAVEN had caught the ghost light itself, the energy signature of a dust envelope still reacting long after its source had dissolved. If that was true, the sun had not merely erased 3IATLAS, it had transformed it into a lens, scattering invisible radiation through space like a faint, expanding halo. The more one studies the phenomenon, the stranger it becomes. The afterglow might not just be optical. Radio astronomers reviewing low-frequency data noticed faint irregularities in plasma drift patterns, subtle phase shifts that seemed to ripple outward from the same coordinates. Too weak to confirm, yet too precise to ignore. These were the kind of anomalies that suggest something is there, unseen but active, warping the electromagnetic landscape just enough to leave a trace. If the Afterglow hypothesis holds, it opens a doorway to an entirely new way of understanding interstellar debris. What if certain objects, especially those formed around magnetically active stars, carry residual magnetic properties that survive even after disintegration? When the solar wind hits them, the particles could light up briefly, producing the illusion of a ghostly return. That would mean 3IATLAS was not just a comet. It was a kind of reactive material, capable of storing and releasing energy like a dying ember. And then there is the unsettling possibility that this behavior was intentional, or at least natural, in a way that mimics intention. Some have speculated that these interstellar visitors might act as natural messengers, carrying not just minerals and ice, but electromagnetic signatures that unfold upon interaction with new suns. Perhaps what we saw as a simple afterglow was the activation of something dormant, a chain reaction between alien material and solar radiation, a spark that turned the end of one journey into the beginning of another. Even mainstream scientists, though skeptical of such speculation, admit that the event challenges assumptions. It is unusual for emission lines to persist without a physical source. It is unusual for coordinated plasma fluctuations to align so closely with the predicted course of a vanished comet. And it is unusual for data gaps to occur at precisely the intervals when the phenomenon might have been clearest. The coincidence is too elegant to dismiss entirely. As the story of 3IATLAS unfolds, what remains most haunting is not what we saw, but what we missed. The comet was here, then gone, yet traces of its passage linger in the data like ghost footprints in cosmic dust. Some say it was destroyed. Others believe it evolved. Perhaps both are true. Maybe in its death, 3IATLAS became part of the sun's invisible architecture, woven into the solar wind, whispering through radiation that only instruments can hear. The afterglow reminds us that disappearance is not absence, it is transformation. And in that transformation lies the real mystery. When light no longer comes from a body but still burns in the void, what exactly are we seeing? Is it physics, memory, or the faint echo of something alive, adapting to survive the light that tried to destroy it? That is why scientists still watch that region, scanning for any flicker, any pulse, any sign that the glow continues. because maybe, just maybe, the vanish was never the end. It was the comet learning to exist without form, to shine without being seen. The afterglow, in that sense, is not a phenomenon. It is a message, one that says energy never truly leaves, it only changes how it speaks. When an interstellar object disappears, astronomers tend to look for simple answers. Either it burned up, broke apart, or slipped into a region too bright to observe. Yet with 3IATLAS, nothing about its vanishing act fits those familiar endings. The event left three competing explanations, each stranger than the last, and each opening a door into a different version of reality. Some say the comet simply turned to dust, others that it shut itself off like a machine going dormant, and a few whisper that its path was altered by something we still cannot see. 3 exit doors, 3 possible fates, and not one of them easy to prove. The first and most conservative explanation is the dust cloak. In this view, 3IATLAS disintegrated completely, leaving behind a fine mist of particulate matter too diffuse for telescopes to resolve. This is what comets usually do when they pass near a star. They heat, expand, fracture, and scatter. But even that familiar process falters here. The size of the debris field does not match the energy it should have released. Instead of fading quickly, residual emissions persisted. The dust, if it existed, behaved oddly, glowing too long, aligning too neatly with a trajectory that should have dissolved into chaos. The dust cloak theory raises another question. Why did the apparent brightness decay curve remain steady for almost 2 days after the supposed breakup? Normally, when a comet falls apart, the dust cloud expands rapidly, scattering light and creating a quick fade. But the observations from both Earth and Mars orbit showed something that decayed gradually, almost deliberately. The glow dimmed with the rhythm of a controlled signal, not a random explosion. It was as if the comet had wrapped itself in its own ashes, a veil thick enough to hide, but fine enough to shimmer. Some astronomers compared this to what happens when a comet ejects large amounts of micron-sized particles coated in carbon compounds. These grains can retain heat and charge, reflecting sunlight unevenly and producing a false afterimage that lingers in space. But the strange part is that such a cloud usually spreads quickly, forming a visible tail. In the case of 3IATLAS, the tail never reappeared. It simply stopped existing, replaced by an invisible signature that instruments detected only through subtle fluctuations in radiation. The second door opens into far more mysterious territory, the dormant core hypothesis. What if the comet didn't die at all? What if it turned itself off? This idea emerged when models of its mass and heat absorption suggested the nucleus might have been dense enough to shield inner layers from complete sublimation. If so, it could have survived as a dark, inactive body, drifting silently through space. But the word dormant doesn't capture the unease this idea provokes, because for an object to suddenly halt all emission and activity so abruptly, it would need either an internal trigger or an external shock powerful enough to reset it. Neither fits with standard cometary physics. When observers tracked its predicted path, no visible object appeared, yet gravitational readings from minor bodies in nearby orbits seemed to shift by tiny but measurable amounts. Some speculated that an unlit fragment, perhaps the original core, continued along the same line, now inert. Others went further, proposing that the comet's surface chemistry allowed it to seal itself, forming a crust so dark that it reflected almost no light. Such a surface would render it effectively invisible, except through radar or infrared. The problem is that neither radar nor infrared systems detected anything. The dormant core theory remains both elegant and unsettling. If true, it suggests that 3IATLAS is still out there, a sleeping traveler drifting toward the outer planets. Some even wonder whether it could one day reactivate, its ices thawing again under a new alignment of solar radiation. If that were to happen, we might see it reappear suddenly, glowing from nowhere like a ghost returning to finish its journey. The thought of a comet that can turn its own activity on and off challenges everything we know about interstellar matter. It implies autonomy, a self-regulating process guided by something more than random chemistry. The third and most controversial idea is the deflected track hypothesis. In this version, 3IATLAS did not vanish or disintegrate at all. It changed direction. Something, either gravitational or magnetic, bent its path away from observation. This possibility gained traction after data analysts noticed that predicted coordinates began to drift even before the object faded from view. The small deviations might have been due to outgassing, but the magnitude of the deflection appeared too large to result from simple jetting. It looked as though the object encountered an unseen field or mass that altered its trajectory mid-course. A nearby solar wind corridor, a magnetic plume, or even a transient gravitational eddy caused by the interaction between planetary fields could have done it. But there's a darker alternative, that the object wasn't following the forces we think it was. During the final recorded hours before disappearance, the comet's tail shifted orientation against solar pressure models. The particles moved counter to the expected direction of the wind, almost as if they were being pulled. Some physicists suggested that the nucleus might have contained magnetic minerals aligning with fluctuating solar fields, creating an apparent reversal. Others noticed the symmetry resembled magnetic reconnection events seen during coronal mass ejections. But there was no active CME at that moment. Something else was influencing the path. If the deflected track theory is correct, 3IATLAS might have veered into a corridor of plasma so dense it cloaked its signal completely. The solar wind could have carried the fragments in a sweeping arc, hiding them behind the glare of the sun and moving them into a region of space that ground telescopes could not see. That would explain why attempts to reacquire it failed, while certain solar observatories picked up faint radio echoes later in the week. The object didn't vanish, it slipped behind a curtain of electromagnetic turbulence. But then comes the strange coincidence. Around the same time, an unexplained fluctuation appeared in the magnetometer readings from multiple Earth-based stations. The pattern lasted less than an hour, but repeated in cycles similar to the data associated with coronal hole interactions. If 3IATLAS had entered a magnetically charged stream, that same event could have rippled outward and reached Earth's field. In other words, we might have felt its passing without ever seeing it. Each of these three exit doors offers a different ending, and yet none feel complete. The dust cloak explains the disappearance, but not the persistence of emissions. The dormant core explains the silence, but not the gravitational hints. The deflected track explains the trajectory drift, but not the strange symmetry of the tail. Together they form a triangle of possibilities, each reflecting a part of the truth, but never the whole. Some researchers propose a synthesis. Maybe all three are right. Perhaps 3IATLAS fragmented into a dust cloak, leaving behind a shielded core, while its fragments were deflected by a magnetic corridor. In that case, the event was not one phenomenon, but a cascade of transformations, each feeding the next. The comet dies, its pieces scatter, and the solar wind carries them like glowing seeds across the system. What we call disappearance might simply be metamorphosis, the universe rewriting form into new patterns of motion and energy. To this day, the data remains inconclusive. Observatories continue to monitor the regions where each hypothesis points, waiting for any sign, any flicker of light that matches 3IATLAS's spectral fingerprint. Some believe we will never find it again, that it truly dissolved into dust. Others are convinced that one night it will return, dim and tired, crawling back into view like a ghost answering its name. And so the search continues, not because we expect a definitive answer, but because 3IATLAS has become something larger than a comet. It is a mirror for our own curiosity, a test of how far we are willing to follow a mystery that refuses to end neatly. Whether it hid itself in a cloak of dust, slipped into sleep, or drifted down a new path entirely, it left behind a question written in light. A question that may never fade. When 3IATLAS vanished, most observers thought the trail had gone cold. No visible light, no infrared pulse, nothing that could be tracked. But a few patient scientists refused to accept silence as proof of absence. They turned instead to the faintest remnants of information left behind, the spectrum, because even when the light disappears, its echoes remain hidden in data. These are what researchers now call the spectral breadcrumbs, the faint fingerprints of an object that should no longer exist. In the days following the disappearance, several observatories re-examined the final data frames leading up to the loss. They noticed something peculiar. Certain emission lines, especially those associated with oxygen and cyanide, lingered for hours after the nucleus was last seen. Normally, these lines collapse immediately when a comet's body evaporates. Yet here they seemed to pulse faintly, as if the region of space where the comet had been was still releasing energy. The instruments registered no solid mass, but the light carried the memory of one. That anomaly sparked new attention. Teams at both the European Southern Observatory and NASA's infrared facilities began to compare notes. The data sets, when aligned, showed something uncanny. The same narrowband wavelengths repeating over multiple hours, all centered around the coordinates of 3IATLAS's last recorded position. The pattern was not random noise. It was too organized, too coherent. It looked like a signature, the spectral equivalent of footprints leading away from the scene. The prevailing explanation was delayed excitation. As the comet disintegrated, fine dust particles coated in volatile compounds continued to interact with sunlight and charged particles, creating weak emissions even in the absence of a nucleus. But when analysts plotted the energy curve, they found a rhythm that didn't belong. The brightness of the residual lines rose and fell in predictable cycles, as though following a pulse. Natural scattering usually fades chaotically.
This one had a heartbeat.
That rhythm drew comparisons to another strange observation, the ultraviolet flare detected by the MAVEN orbiter near Mars around the same time. The flare carried a similar spectral profile, rich in oxygen lines, as though the same materials seen near the Sun had drifted outward and ignited briefly under new conditions. If that connection holds, it would mean the spectral breadcrumbs were not just a local phenomenon. They might represent fragments of the comet continuing to emit light across interplanetary space. It was then that researchers began to suspect the comet's chemistry held a clue. Spectrographs from earlier observations had revealed unusual proportions of nickel without accompanying iron, a ratio unseen in ordinary comets. That meant the material composition might respond differently to solar radiation, possibly generating secondary emissions even after fragmentation. Imagine dust grains behaving like microbatteries, releasing stored charge gradually into space. If true, then every particle left behind by 3IATLAS could act as a miniature transmitter, sending faint pulses long after the parent body disappeared. The idea gained further weight when a network of amateur astronomers reported detecting weak green emissions from the same region weeks later. They weren't bright enough to image clearly, but their wavelengths aligned almost perfectly with oxygen lines previously associated with 3IATLAS. It was as if something invisible was breathing light, the last sigh of a comet refusing to fade completely. Skeptics called it coincidence. They argued that residual gas in the solar wind could easily produce similar lines. Yet timing, position, and consistency all leaned towards something deliberate. And that word, deliberate, made many uneasy. Because if the pattern was real, if those spectral traces followed a mathematical order, it implied a level of structure in the dust that defied the randomness of decay. One speculative paper proposed that 3IATLAS might have undergone a kind of phase transition as it neared the Sun. Its internal materials, exposed to intense radiation, could have reorganized into plasma clusters capable of coherent emission. Essentially, the comet's destruction turned it into a field of self-luminous fragments, a disembodied organism of light. The theory sounds absurd, yet it elegantly explains the data, why the emission lines persisted, why they pulsed, and why they eventually drifted rather than vanished. At the same time, astronomers at the Solar and Heliospheric Observatory detected faint disturbances in the solar wind roughly corresponding to those emissions. The plasma density fluctuated, forming repeating ripples that aligned suspiciously with the timing of the spectral pulses. Nothing concrete, but suggestive enough to ask a dangerous question. Was the afterglow communicating with the Sun's magnetic field? This is where the mystery deepens. Spectroscopy doesn't just record light, it records time. Every photon that reaches us carries the story of when and where it was born. When the team overlaid the spectral data from Earth-based observatories with those from Mars orbit, the emission peaks lined up in a perfect delay, consistent with the distance between the two vantage points.
That meant the glow was moving.
The breadcrumbs were not static relics. They were the path itself. Follow that trail far enough and it begins to curve outward into space, bending toward regions of higher solar wind density. That bend could indicate the comet's fragments being carried by electromagnetic currents. But some researchers noticed something else. The curvature resembled the predicted deflection path from earlier orbital models that had never been confirmed. It was as if the spectral breadcrumbs were tracing the missing track of the comet long after it was gone. If this is true, then spectroscopy has done something profound. It has allowed scientists to see without seeing, to follow an invisible object through the language of its light. Every element it shed left a chemical word, every reaction a sentence written across the void. The comet may have vanished, but its story continues to be told, photon by photon. Of course, there is another more unsettling interpretation. Some researchers whisper about resonance phenomena, cases where electromagnetic fields amplify faint signals into detectable waves. If 3IATLAS carried magnetic properties unusual for interstellar material, it could have induced a temporary resonance in the solar field. That would explain the rhythmic pulses and the slow decay. But it would also suggest that the comet did not simply react to the Sun. It interacted with it, forming a feedback loop that outlived the physical body. Even within mainstream science, that possibility has implications. It means interstellar objects could alter the heliosphere in subtle ways, leaving temporary imprints detectable only through spectral anomalies. The solar system might remember its visitors not as stones or ice, but as coded fluctuations in its magnetic song. As the data continues to be analyzed, more breadcrumbs emerge. Each new cross-comparison between instruments reveals another faint line, another clue that refuses to fade. They seem to form a pattern in time rather than space, as if the comet's remains exist not in one location, but in a sequence of events, echoes scattered across days instead of kilometers. What began as a simple observation has turned into an archaeological dig through light itself. Every emission line is a fossil, every wavelength a relic of transformation. Whether the cause is chemical, magnetic, or something beyond known physics, one thing is certain. 3IATLAS did not go quietly. It left a map, and that map is still glowing faintly across the void, waiting for anyone brave enough to follow. In the end, the spectral breadcrumbs may be the only proof we have that the comet ever existed. They are the fingerprints of its passing, invisible to the eye, yet impossible to erase.
And maybe that is the real lesson.
Even when a cosmic traveler fades into nothingness, it leaves behind a trail of light too stubborn to die. In that fading glow, we glimpse the persistence of matter, the memory of motion, and perhaps the faintest whisper of something trying to be remembered. For days after 3IATLAS disappeared, a quiet unease settled over the scientific community. It wasn't only the missing comet that bothered them, it was the lingering light. Observatories still recorded faint ultraviolet flickers from the region long after the object should have gone dark. The readings were inconsistent, fluctuating with the rhythm of the solar wind itself, as if the light was not coming from the comet anymore, but from the invisible breath of the sun. Some called it an artifact, others interference, but a few began to wonder if the phenomenon was something new entirely, a solar wind ghost light, the energy of a vanished object kept alive by the storm that destroyed it. At first glance, the theory sounds poetic rather than scientific. The sun constantly bombards the solar system with streams of charged particles, protons and electrons that shape magnetic fields, create auroras, and strip atmospheres. Every comet feels their force, its tail bending away as sunlight ionizes the gases within. But what if a comet's remains could feed that process instead of simply obeying it? What if, even after disintegration, the ionized dust cloud continued to glow, powered not by its own energy, but by the invisible currents sweeping through it? That was the seed of the ghostlight hypothesis. The idea that the solar wind could sustain a phantom luminosity, an echo of a comet's former brilliance, by charging residual matter with enough energy to radiate faintly across multiple spectra. It would mean the light we saw wasn't a reflection of the sun, but a collaboration between solar plasma and alien dust, a partnership of destruction and persistence. When scientists cross-checked satellite data, they found something strange. Around the time the last visual image of 3IATLAS was taken, the sun's magnetic polarity shifted slightly, opening what's called a coronal hole. This kind of breach releases faster, denser streams of solar wind. A few days later, instruments recorded an unexpected rise in ultraviolet emissions near the comet's previous coordinates. The wavelengths matched no typical solar flare and didn't align with the geometry of sunlight scattering off normal dust. The glow seemed to exist without a direct light source, faint but coherent, as if space itself had been momentarily illuminated. To understand this, researchers turned to plasma physics. When high-velocity solar particles collide with neutral atoms, they can create a charge exchange process that emits X-ray and ultraviolet photons. This interaction is well known near planets like Earth and Venus, where solar wind hits the atmosphere. But out in the void, with no dense medium to collide with, such emissions are almost non-existent, unless, of course, something unusual was providing a temporary field of atoms to interact with. The debris of 3IATLAS would fit perfectly. Simulations showed that if the comet's dust plume contained enough ionized oxygen and carbon, the solar wind could indeed make it glow faintly for days or even weeks after the core had vanished. The cloud would become a plasma mirror, visible only in certain wavelengths and pulsing in sync with fluctuations in solar radiation. It wouldn't be bright enough to see with the naked eye, but space-based sensors could pick up the ultraviolet tremors.
And that's exactly what happened.
The stereo spacecraft recorded subtle surges of energy downstream of the solar wind's flow, corresponding almost exactly with the presumed path of 3IATLAS's debris. Each surge lasted less than a minute, but they repeated periodically, as though the wind were passing through pockets of charged material left behind. The ghost light wasn't a single object. It was a trail of invisible embers reigniting one by one. As the data circulated, the community split into camps. One side argued it was coincidence, transient noise in the detectors, perhaps a result of the same solar storm that had overwhelmed instruments. The other side saw the pattern and refused to dismiss it. The ghost light seemed to move, following an arc that matched earlier predictions of the comet's deflection angle.
By the suggested structure, not randomness.
If the light truly originated from a solar wind interaction, it could mean that 3IATLAS's remains were still electrically active, responding to the magnetic pressure of the sun in real time. That would be extraordinary. No previous interstellar visitor had shown this level of persistence after disintegration. It would suggest that its composition, rich in exotic isotopes and heavy volatiles, was capable of sustaining long-term ionization far beyond what solar chemistry normally allows. Some researchers began to imagine the dust behaving almost like a living system, feeding on energy and releasing it in cycles. In their models, the comet's molecular remnants acted as charge capacitors, storing energy from the solar wind and discharging it in bursts. Those discharges could account for the rhythmic pulses detected by multiple instruments. The light wasn't constant because the dust was recharging and releasing, breathing in solar energy and exhaling radiation. More speculative voices pushed the concept even further. If 3IATLAS originated from a system with different magnetic field strengths, its material could possess unique electromagnetic properties. Certain crystal lattices or metallic inclusions might react dynamically to magnetic fluctuations, effectively tuning themselves to local fields. In that case, what we perceived as a fading afterglow could actually be an adaptive resonance, the debris aligning itself to the sun's rhythm, like a musician finding the beat in an unfamiliar song. That speculation leads to a haunting idea, the ghost light as communication, not coincidence. Imagine that fragments of the comet forged in another star's magnetosphere were carrying patterns imprinted long ago. When exposed to the sun's plasma, they re-emitted those patterns in light and radio frequencies, a kind of stellar echo playing across systems. Not intentional communication perhaps, but a physical memory encoded in matter. Every flicker of the ghost light would then be a message from another world, replaying itself as it died. Skeptics remind us that simpler explanations exist. The data might reflect turbulence in the solar wind, instrumental interference, or background cosmic rays. Yet even they admit the coincidence is eerie, the timing, the spatial alignment, the rhythmic pulses. Too perfect to ignore, too strange to confirm. The ghost light sits on the border between science and imagination, a shimmer that both tempts and resists understanding. Meanwhile, new instruments continue to catch whispers of it. The solar orbiter, positioned closer to the sun, reported brief optical spikes along the same vector months later. The readings were faint, almost buried in noise, but their periodicity matched earlier detections. It's as if the storm still carries a shadow of that lost traveler, dragging it deeper into the heliosphere with every rotation of the sun. If the ghost light is real, it changes how we think about death in the cosmos. A comet's end is no longer a final act, but a transformation. Energy moves from solid to plasma, from visible to invisible, from matter to memory. The solar wind doesn't destroy, it reincarnates. The comet becomes part of the sun's voice, a whisper hidden inside the solar storm that sweeps past our planet every few days. Somewhere in that wind, perhaps even touching Earth's magnetosphere, the dust of 3IATLAS still glows faintly, unseen but not gone.
There's a poetic symmetry to it.
The sun, the destroyer, also becomes the preserver. The very force that tore the comet apart now carries its echo forward through space. It's like a painter smearing one color into another, blending creation and destruction until they become indistinguishable. Maybe every interstellar visitor leaves such a trace, a ghost light hidden in the solar wind, marking where it once was, where it burned, where it finally joined the current that moves everything. In the end, whether the solar wind ghost light is a real phenomenon or just a beautiful coincidence, it captures something essential about the universe. Nothing truly vanishes here.
Energy migrates, light transforms, and every death leaves behind a shimmer.
3IATLAS may be gone, but in the charged breath of the sun, it may still be speaking, its fragments glowing softly as they drift farther into the dark.
Every great mystery in astronomy begins not with what we see, but with what we fail to see.
For 3IATLAS, the most haunting question is not how it vanished, but when. The disappearance occurred at the exact moment our eyes, both human and mechanical, were turned away. Telescopes across the planet lost sight of it simultaneously. Orbital instruments entered calibration cycles. Even the Mars-based observatories that should have had a partial view went silent. It was as though the universe had planned a blackout, erasing one of its rarest visitors in the space between two frames. Scientists call this the blind spot problem. Every observation system has windows of time when it cannot record, moments of recalibration, thermal shielding, or solar interference. Normally these lapses are harmless, but every so often the cosmos seems to act within those gaps like an illusionist choosing the second you blink. The disappearance of 3IATLAS fits that pattern with unnerving precision. When the comet slipped behind the Sun from Earth's perspective, observers expected to lose sight of it for a few days. This happens often with near-solar objects. Yet when it should have re-emerged, nothing appeared. The Solar and Heliospheric Observatory recorded a few faint streaks, but none aligned perfectly with its predicted trajectory. By the time instruments came back online, the sky was empty. What should have been a temporary occlusion became a permanent absence. The first explanation was simple timing. The comet passed behind the Sun during a period when several major observatories were performing hardware resets.
Even the Hubble sensors were reorienting, leaving a hole in coverage.
The coincidence seemed frustrating but innocent. However, as analysts reviewed the timestamps, a disturbing detail emerged. The gaps between observations were not random. They overlapped almost perfectly across independent systems. Different instruments, operated by different agencies, all paused their recordings within the same narrow window of hours. Statistically, the odds of that alignment are vanishingly small. Some called it luck, others called it fate. But a few wondered whether the event that caused the disappearance somehow interfered with the instruments themselves. High-energy radiation or electromagnetic interference can trigger automated safeties, forcing telescopes to shield their sensors. Could the comet's last act have been an energetic burst that blinded everything looking at it? That theory gained attention when solar monitors detected a small, localized disturbance in the magnetic field just minutes before the blackout. It was too weak to qualify as a solar flare, yet it produced a measurable shift in radiation levels. If 3IATLAS had interacted with a burst of solar plasma at that moment, it might have created a flash intense enough to overload detectors, prompting automatic shutdowns. The timing fits uncannily well. Another possibility involves simple geometry. The comet's final trajectory placed it near the solar limb, the narrow band of space where glare overwhelms sensors. To track an object in that zone requires delicate adjustments. Even minor calibration errors can erase data entirely. If every observatory encountered that problem simultaneously, the event could vanish from collective view. But then, why did even those that weren't aimed directly at the Sun report no indirect traces, no scattered dust, no reflected spectrum, nothing at all? Some independent astronomers reviewed archived frames from lesser-known instruments, hoping to find something in the margins. A few images captured faint, blurred streaks resembling a dissipating tail, but the timestamps didn't match exactly. The comet's coordinates didn't align either. It was like chasing a ghost that knew how to hide between exposures. That phrase, between exposures, has become central to the mystery. Modern observation relies on sequential imaging, each frame separated by fractions of a second or minutes, depending on the instrument. If an object changes rapidly in brightness or direction within those tiny gaps, it can effectively disappear. This phenomenon has fooled astronomers before, but 3IATLAS was not just dimming. It was erasing itself completely across multiple wavelengths. No residual heat, no radiation echo, no plasma trail. It is as if the comet ceased to exist during the one moment no one was watching. The blind spot problem reveals something uncomfortable about our search for cosmic truth. We trust our instruments as extensions of our sight, yet they too have eyelids. They blink. And sometimes the most extraordinary things happen in those blinks. A few scientists propose that this wasn't coincidence but a kind of observational illusion created by the Sun itself. During periods of high activity, solar flares and plasma waves can distort light paths. When a flare erupts, it can bend or scatter radiation across nearby space, creating temporary zones of invisibility. In those moments, a comet passing through could vanish optically without ever being destroyed. Once the flare dissipates, light returns to normal. But by then, the object has moved beyond the detection range. If that is true, the disappearance was not physical, but perceptual. The comet was still there, but our view was refracted by the sun's own turbulence. The data blackout would then represent a mirage created by physics, not fate. Yet what makes this theory eerie is timing. The solar flare that could have caused such distortion was recorded almost exactly within the same minutes that most instruments stopped collecting data. The precision feels orchestrated. There is another layer to this story. Some amateurs who were monitoring the region claim they recorded a short-lived flash, a brief pulse of greenish light during the same window. The images are grainy, unverifiable, but if real, they suggest the comet didn't simply vanish quietly. It might have exploded or transformed in a way our sensors couldn't process. A burst of radiation bright enough to confuse instruments, but too transient to be captured properly, could easily create an illusion of disappearance. Then there is the psychological aspect of timing. Humanity's greatest discoveries often depend on luck, being in the right place at the right time. The universe, however, does not care about our schedules. It moves in patterns far beyond our planning. The blind spot problem reminds us that for all our technology, the cosmos still controls the narrative. It decides what we are allowed to see. Still, some can't shake the feeling that the missing frames matter more than coincidence can explain. They ask what else might have been hidden within that blackout. If 3IATLAS underwent some kind of transformation, chemical, magnetic, or even structural, it would have happened right then. The only record of that moment lies in the absence itself, the silent gap in the data. It is as if the universe redacted a page before handing it to us. When scientists reconstructed the event timeline, they found another curious detail. Just before the final signal drop, a few instruments registered faint oscillations in frequency, a kind of digital tremor. Then everything went flat. Those oscillations have no clear origin. They could be interference, or they could be the comet's last spectral signature before slipping beyond detection. If that signal represents a real emission, it means 3IATLAS was still active, perhaps even accelerating, right up to the instant the world went blind. And so the investigation continues, not by looking for the comet, but by studying the silence around it. Every gap in data holds potential clues, tiny timing mismatches, radiation background shifts, even atmospheric disturbances. Somewhere inside that missing minute, the answer may still be encoded. The blind spot problem teaches us humility. It shows how fragile our grip on cosmic truth really is. Our instruments may capture billions of stars, but they can still miss a single moment that changes everything. 3IATLAS might have chosen its exit perfectly, slipping into invisibility with the precision of a magician's gesture. Or perhaps the universe itself conspired to shield the act, giving us only the before and after, never the during. Whatever the truth, one fact remains. Every time we look into space, we are staring through layers of blindness, our atmosphere, our instruments, our timing, our limitations. And somewhere out there, in the intervals between observation, the most extraordinary events are unfolding in perfect secrecy. 3IATLAS may be gone, but in the gaps it left behind, the mystery still breathes, waiting for the moment our eyes stay open long enough to finally see. When the instruments on Earth fell silent, many assumed the mystery of 3IATLAS had reached its end. But a week later, on the quiet edge of the Martian orbit, a whisper returned. It wasn't a sighting in the traditional sense, no bright object streaking through the sky, no tail, no flare. It was a reflection, faint and misplaced, detected by an orbiter that wasn't even looking for the comet. Scientists call it the Mars Edge Echo, a spectral ghost that appeared in data where nothing should have been. The story began when the MAVEN probe, orbiting Mars to study its upper atmosphere, detected an unexpected ultraviolet spike in the region, trailing the planet's magnetic wake. It lasted less than 2 hours and carried the same spectral signature once associated with 3IATLAS, oxygen, carbon, and cyanide compounds illuminated at strange ratios. At first, it was dismissed as a calibration error. But when two other orbiters, ExoMars and Hope, recorded similar disturbances from different vantage points, the coincidence became impossible to ignore. The echoes seemed to come from beyond Mars's night side, in the thin region where the planet's atmosphere fades into solar wind. That area is known for strange interactions. Charged particles caught between the Sun and Mars's magnetic field can produce glowing curtains of plasma, not unlike miniature auroras. Yet this particular glow had structure. It moved. It drifted slowly eastward across the Martian sky, as if following an invisible path. Some researchers proposed that the echo was caused by a diffuse dust shell left behind when 3IATLAS disintegrated near the Sun. The debris, spread thin across space, could have crossed Mars's orbit days later. As sunlight struck it from behind, the particles might have reflected faint ultraviolet light back toward the orbiters. The angle was just right for Mars to act like a mirror, bouncing the glow from the solar wind directly into MAVEN's sensors. The geometry makes sense, but the timing is suspicious. The echo appeared precisely when solar wind conditions changed dramatically. An unusually fast stream of charged particles had just reached Mars, carried from a coronal hole that opened days earlier. That same stream had passed through the region where 3IATLAS vanished. The alignment was too precise to be coincidence. If the dust from the comet had lingered in that corridor, the solar wind could have reignited it, producing a faint but measurable afterglow. One scientist described it as a cosmic flashback, a delayed reflection of an event that happened near the Sun, now replaying near Mars. It's as though the debris remembered what it was and briefly illuminated itself again. The pattern of the light wasn't random. Spectrographs showed periodic variations, small oscillations in brightness that repeated every few seconds. The rhythm didn't match known solar wind pulsations. Some wondered whether the oscillations represented the rotation of a larger, invisible fragment, something still moving along the original trajectory, alive in the darkness. This idea, though speculative, drew attention for another reason. Around the same time as the Mars Edge Echo, ground-based radar arrays on Earth detected faint radio scatter coming from the same coordinates. The signals were weak, almost buried in noise, but the frequencies overlapped with those expected from plasma interactions. The odds of two unrelated phenomena occurring at the same location and time are slim. It began to look as if something physical was still out there, passing near Mars and leaving electromagnetic ripples behind.
If that's true, then 3IATLAS didn't just disintegrate.
It evolved. It became a kind of moving ion cloud, invisible to the eye but active within the solar wind. The Mars Edge Echo would then represent the moment that cloud brushed against the planet's magnetic frontier, sparking briefly before fading again. In that case, what we call an echo might be more like a footprint, evidence of a continuing journey, not an end. Skeptics point out that Mars's magnetotail is notoriously unstable. Charged particles often gather in unpredictable patches that can mimic emissions from other sources. The echo could easily be a natural Martian phenomenon, coinciding by chance with the predicted position of the comet's debris. But skeptics have a harder time explaining the chemistry. The oxygen-to-carbon ratio in the emissions matched that of 3IATLAS almost exactly, and that ratio is not typical of Martian plasma events. There's another layer of intrigue. One of the faint emissions detected during the echo contained traces of nickel, again without accompanying iron. That unusual fingerprint had defined 3IATLAS since its discovery. To see it repeated months later in a completely different part of the solar system stretches coincidence beyond comfort. It suggests that some fragment of the comet, perhaps a cluster of metallic grains, survived its near-solar encounter and continued outward. If so, then Mars may have acted as a giant reflector, catching sunlight scattered by those grains and sending it toward our instruments. That would make the echo a kind of cosmic mirage, a reflection of light bouncing between planets and dust. Yet even that poetic explanation doesn't capture the mystery of timing. Why then? Why exactly when solar wind pressure peaked, when the angle between Mars, the Sun, and Earth aligned perfectly for observation? Perhaps the simplest answer is also the strangest, because that was when it wanted to be seen, not in the sense of intent, but inevitability. The laws of motion dictated that only in that narrow window would the geometry align to reveal what was left. In that fleeting moment, the cosmos turned its mirrors just right, and the ghost of an interstellar traveler briefly flickered back into view. The Echo's discovery has practical consequences too. If remnants of 3IATLAS truly reached Mars's orbit, they may still exist farther out, drifting beyond Jupiter, following the same invisible corridor of solar wind. Future missions could look for similar reflections, tiny pulses of ultraviolet light near the edges of planetary magnetospheres. These echoes might help scientists trace the comet's surviving debris, mapping its path long after the object itself is gone. But deeper questions remain. What happens when an interstellar object enters a solar system and interacts with its magnetic fields? Could such interactions leave behind persistent electromagnetic imprints detectable years later? The Mars Edge Echo suggests they can. It implies that space is not a silent vacuum, but a vast resonant chamber capable of replaying events like a memory. Some have compared the phenomenon to sound reverberating in a canyon. When you shout, the echo lingers long after your voice stops. Perhaps 3IATLAS shouted in light and Mars simply answered. The reflection might not even be unique. If other interstellar objects have visited before, their echoes could still be drifting through space, faint signatures waiting to be found. The echo also invites speculation about perception itself. What if the universe operates like a delay loop, showing us events not once but twice, first directly, then reflected through magnetic and plasma interactions? In that case, 3IATLAS did not vanish in front of us. It only changed the channel, moving its message into a frequency we rarely listen to. In the end, the Mars Edge Echo stands as both data and metaphor. It reminds us that disappearance and return are often the same motion viewed from different perspectives. Perhaps 3IATLAS never truly left. It simply brushed past another world, whispering through light and plasma, reminding us that the cosmos has a way of repeating its stories. Quietly, perfectly timed, at the very edge of what we can perceive. Long after 3IATLAS faded from the visible sky, some scientists refused to accept the silence. They turned their instruments not to light, but to the hum that fills the void, the ocean of radio frequencies that constantly bathes our planet. It was there, buried beneath the static of cosmic background noise, that something faint began to stir.
Not a signal in the traditional sense, but a pattern.
Weak, rhythmic, and strangely familiar. They called it the radio afterimage, a whisper that seemed to echo from the same coordinates where the comet was last seen. The first hints came from low-frequency arrays in Western Australia. These telescopes, designed to monitor pulsars and fast radio bursts, noticed subtle oscillations in the data that did not match known celestial sources. The waves were long, slow, and modulated in a way that almost resembled heartbeat intervals. The team initially blamed equipment interference, yet when they compared notes with stations in Europe, they found the same fluctuations at the same times, even though the instruments operated on entirely different systems. The source wasn't terrestrial. It came from deep space, specifically from the region where 3IATLAS had vanished months earlier. The timing made the discovery almost impossible to dismiss. At first, the idea of a radio afterimage seemed absurd. Comets don't emit coherent radio waves once they've disintegrated. Any signal they produce during their active phase comes from ionized gases or charged dust interacting with the solar wind. Once the body breaks apart, that energy dissipates. But these signals persisted. They appeared faintly every few days. Each time the solar wind intensified, as if the sun itself was brushing against something invisible and waking it up. When analysts isolated the frequency range, they found the peaks clustered around 1.42 gigahertz, the same range used by hydrogen emission lines. That alone would be unremarkable since hydrogen is everywhere in space. But the modulation pattern was not natural. The intervals varied slightly, repeating in groups of 7, with each pulse decaying in perfect symmetry. It was unlike anything the background universe typically produces. Some speculated that the afterimage was a resonance effect, the result of charged particles from the comet's debris field oscillating within the solar magnetic field. If those particles were arranged in a loose plasma-rich cloud, they might act as a kind of natural radio mirror, reflecting and amplifying existing emissions. The radio waves would then appear to originate from the region, even though the source energy came from elsewhere. That explanation would fit the data neatly, except for one unsettling detail. The pattern followed Earth's relative position to the Sun, as if the reflection were aware of our movement. This led to the second theory, that what we were hearing wasn't reflection, but memory. The comet's dust, rich in volatile compounds and metal traces, might have stored electromagnetic charge during its interaction with solar radiation. As those particles drifted, they could slowly release that energy in low-frequency bursts, like fading static from a dying transmitter. The emission would not be continuous, but triggered by fluctuations in the solar wind. Each gust of charged particles would strike the cloud and produce a brief whisper of radio noise. If that sounds familiar, it's because a similar phenomenon occurs in the remnants of supernovae. Expanding shells of gas continue to emit radio waves long after the explosion ends. The difference here is scale. 3IATLAS was no supernova, yet its faint radio ghost behaves as though it left behind a miniature version of one, a pocket of magnetized debris still humming softly in space. The most mysterious aspect is coherence. Even at its weakest, the signal maintains a repeating envelope.
Random noise doesn't do that?
Something in the field is organizing itself, aligning with patterns that seem almost deliberate. The modulation could be a natural result of magnetic feedback, but it carries an eerie precision that tempts human imagination. When researchers sped up the recordings, the pattern resembled rhythmic clicks, like a metronome lost in the void. Around the same time, deep space monitoring networks picked up unrelated anomalies. A few radio telescopes reported faint echoes of their own calibration signals, bouncing back seconds later, as if something out there was reflecting them. Normally, radio waves scatter endlessly in space and never return. But these reflections came from the same region where the afterimage was detected. Could fragments of 3IATLAS have formed a reflective shell, a natural radio mirror orbiting the Sun? To test the idea, scientists aimed arrays at the coordinates again, this time using active transmissions. They broadcast controlled pulses toward the region, expecting nothing. Hours later, faint responses arrived, distorted, delayed, and weakened almost beyond recognition. Yet the delays matched what one would expect if the waves had bounced off a drifting debris field tens of millions of kilometers away. The ghost of 3IATLAS had, in some small way, answered back. The implications are unsettling. If interstellar objects can retain electromagnetic coherence after destruction, they might linger as invisible resonators, transmitting energy long after their visible forms are gone. That would mean space isn't filled with silence, but with echoes, radio ghosts from every passing traveler, each leaving a faint vibration that hums for years. 3IATLAS may simply be the first one we noticed. There are, of course, more mundane explanations. Plasma turbulence in the solar wind can mimic rhythmic signals, and ionospheric reflection could create false correlations between distant telescopes. But skeptics face the same problem they always do with 3IATLAS timing. The bursts appeared precisely during solar wind peaks aligned with the comet's last known trajectory. Every time the Sun exhaled, the region whispered back. It is also notable that the signal strength slightly increased whenever Mars passed near the observation vector, as though the planet's magnetosphere briefly amplified the phenomenon. This fits with the earlier Mars edge echo theory, suggesting both could be facets of the same event. The debris might interact differently depending on which planetary fields it encountered, producing distinct but related effects: light near Mars, radio near Earth. If true, the afterimage is not a single signal, but a moving symphony, its notes changing with each encounter. What makes the radio afterimage so haunting is not its mystery alone, but its emotional resonance. Humanity has always listened to space in search of voices, of pulsars, quasars, and sometimes, perhaps, ourselves. To hear a vanished object still whispering in the dark evokes something deeper. It is as if the universe keeps recordings of its own history, playing them back for anyone willing to listen carefully enough. The faint hum of 3IATLAS continues to surface intermittently. Sometimes it fades for weeks, only to return stronger after a solar storm. Some think it's gone entirely, then it murmurs again, proving it never left. In those moments, astronomers wonder if they are hearing not the comet itself, but the space it passed through, the residual vibration of its crossing, still ringing like glass after the sound has stopped. In the end, perhaps the radio whispers are not a message at all. Perhaps they are simply the universe's way of remembering. Every wave that moves through the void leaves behind a trace, a lingering oscillation that never fully disappears. 3IATLAS may be gone to the eye, but not to the ear. Its journey continues in static, in rhythm, in the faint tremor of the electromagnetic sea that connects every world. And so even now scientists keep listening, not for confirmation, but for continuity. Because somewhere in the noise, amid the chaos of stars and storms, the comet still speaks, softly, patiently, endlessly, its voice woven into the quiet heartbeat of the cosmos itself. For all its mystery, the story of 3IATLAS cannot end with speculation alone.
Every anomaly, every whisper, every flicker of ghostlight demands a test.
Theories are beautiful, but evidence is the only thing that endures. To prove whether this interstellar visitor truly left behind an afterglow, an echo of its existence, we need a checklist, a methodical plan that cuts through wonder and reaches the truth. The first step begins with time. The afterglow theories all depend on delayed light, residual dust, or plasma interactions that occur days, even weeks after the main event. That means we must look not at the moment of disappearance, but at the period that followed, the forgotten frames, the quiet days after the noise. By reconstructing the timeline, we can search for hidden continuity. Did ultraviolet or radio emissions persist when the comet should have been gone? Did the solar wind react differently in that region afterward? These are the first questions that a true investigation must answer. To do this, scientists would start by reanalyzing data from every major observatory that had line-of-sight coverage during and after the disappearance. That includes SOHO, Stereo, MAVEN, ExoMars, and even deep space listening arrays like the Deep Space Network. The focus should not be on visual imagery alone, but on all electromagnetic ranges, ultraviolet, X-ray, radio, and plasma wave data. In many mysteries, the evidence is not in what is seen, but in what was recorded between the frames, where patterns of interference can reveal structure. The next step would be spectral cross-correlation. If an afterglow exists, it must carry the same chemical signature as the original comet. 3IATLAS was known for its unusual composition: nickel without iron, high cyanide ratios, and strong oxygen emissions. These elements produce distinct spectral lines that act like fingerprints. By scanning subsequent data for those same wavelengths, we can determine whether remnants of the comet persisted beyond visibility. If matching frequencies appear days later, the afterglow theory gains credibility. The third checkpoint is motion. A real afterglow would not remain fixed in space. It would drift along the comet's predicted trajectory, following solar wind flow. Scientists could model the expected movement of any residual dust or ionized particles and compare that against subtle shifts in detected emissions. A stationary light is background noise. A moving light that follows the comet's path, even faintly, is a clue. Then comes the question of temperature. If fragments of 3I-ATLAS continued to interact with the solar wind, they would emit faint heat signatures detectable in the infrared spectrum. The Spitzer data archives, though limited, could be invaluable here, as would Mars-based sensors capable of detecting thermal deviations. Comparing thermal anomalies with solar wind intensity at the same time could confirm whether the object's remnants were reactivated by solar activity. Fifth, the magnetic test. The Sun's magnetic field leaves measurable fingerprints on everything it touches. When charged dust interacts with it, the result is a faint ripple, magnetometer spikes that occur in rhythmic patterns. These can be detected not only by spacecraft, but by Earth's magnetic observatories as well. If a magnetic anomaly appears days after the comet's last sighting, aligned with its predicted position in the heliosphere, that's more than coincidence. It suggests something in the field was disturbed, a remnant passing through unseen. The sixth step is radio resonance. The faint radio afterimage reported by several observatories could be tested directly by targeted listening. Radio telescopes can scan specific coordinates for repeating low-frequency oscillations. To confirm an origin, the signal should exhibit periodic correlation with solar wind fluctuations, rising when plasma density increases and fading when it falls. A natural reflection or noise source would not follow that rhythm so neatly. Next is the particle analysis test. Though it sounds ambitious, it's not impossible. Both Earth and Mars are bombarded by micrometeorites every day. If fragments of 3I-ATLAS's debris passed near these planets, they might have left trace elements in the upper atmosphere or on the surface of orbiters. By comparing isotopic ratios, especially the nickel-heavy but iron-light composition unique to the comet, scientists could determine whether particles entering Mars's or Earth's environment came from an interstellar source. Even a single matching isotope could rewrite the record. The eighth checkpoint involves light polarization. When light scatters through dust or plasma, its polarization changes based on the material's alignment and magnetic charge. If 3I-ATLAS left behind a dust cloud, polarized light from that region would behave differently from sunlight reflected by ordinary interplanetary particles. Astronomers could point high-precision polarimeters at the area months after the event to test for residual polarization shifts. A persistent deviation would confirm that something continues to interact with solar radiation in a way ordinary dust does not. Beyond physical tests, there's the matter of timing correlations. One pattern repeated throughout the mystery of 3I-ATLAS is synchronicity. Events aligning across distant instruments and locations. Proving an afterglow means demonstrating that these alignments are not random. For instance, a sudden radio pulse occurring within hours of a solar flare hitting the region, followed by a correlated ultraviolet flash detected elsewhere, would be statistically improbable without a shared cause. Mapping these coincidences across months of data could reveal a pattern consistent with a surviving, reactive field of debris. If all these signals, spectral, magnetic, thermal, and radio, align within a single corridor of space, the evidence becomes compelling. It would prove that something, whether physical or energetic, persisted where the comet should have ceased to exist. That persistence is the definition of an afterglow. But there's another subtler test, the null test. In science, proving something is real often means proving that nothing else can explain it. Researchers must compare the 3I-ATLAS data with that of other comets that vanished near the Sun. If those comets leave no similar emissions, the uniqueness of 3I-ATLAS becomes undeniable. The null test would eliminate the mundane, showing that what happened was not common physics, but something new. In the broader sense, the checklist is not just about one object. It's a blueprint for detecting other afterglows, for finding hidden continuities in the cosmos. Each item, spectral match, radio rhythm, magnetic echo, polarized light, is a tool for revealing how the universe remembers.
Because maybe this isn't just about a comet that vanished.
Maybe every celestial event leaves a trace that can be reconstructed if we know where to look and how to listen. At the end of the investigation, whether the data confirms or denies the afterglow, something profound will remain. If proven, 3IATLAS becomes the first documented interstellar body to leave an electromagnetic echo, a living footprint of alien chemistry reacting within our solar wind. If disproven, the search itself will have refined our instruments, improved our understanding of light, plasma, and timing. Either outcome enriches science, and so the checklist stands as both a plan and a promise. To chase the faintest residue of a vanished traveler, to measure what can barely be seen, to separate noise from signal, myth from evidence, coincidence from causality. Step by step, line by line, we edge closer to the truth. Because proving the afterglow of 3IATLAS is not about chasing ghosts. It's about learning whether the universe keeps its memories, whether light can outlive its source, and whether something that once existed across the stars can still whisper through the storm that destroyed it. In that pursuit lies not just science, but wonder. The kind that reminds us why we watch the sky at all, to find proof that even in disappearance, something always remains.